So I'm presenting the answer key for our first exam. So our first question, you had to identify the carbon to hydrogen mass ratio, which one was closest to 6 to 1. So for each, you wanted to get the mass of your carbon. So for the first one, 2 times 12, 12 coming from the periodic table, for your grams of hydrogen. Now there's 6, each one is 1, so that would be 6. So that would be a ratio of 4 to 1, 24 divided by 6. What you do is you just do that for each one and then find out which one is going to be 6 to 1. The correct answer turns out to be C. You'd have 24 grams of carbon for every 4 grams of hydrogen, and there's your 6 to 1 ratio. Number 2, I went over in class, but just to give you the explanation non-verbally. And you needed to show that work. Number 3, complete combustion of a hydrocarbon. So a hydrocarbon, as I've told you to write it, CXHY. Combustion, it's burning. Will give you 3 moles of water, and it says 2 moles of carbon dioxide. So clearly it's producing 6 hydrogens and 2 carbons. So this formula must have been C2H6. What can we conclude from this mass spectrum? Well, we've got 2 isotopes. Now, what element? So the average would come out to be around here. And if you look at your periodic table, the element with an average around there is antimony, Sb. So that's out. Now this number right here, the 121, is the mass. So you could express this as Sb-121. The mass is equal to the number of protons plus the neutrons. So this 121 is not the number of neutrons. How many neutrons would it have? Antimony, you would need to subtract its number of protons, which is 71. Oh, no, it's not. It's 51. So that's the number of protons. This is the protons plus the neutrons. You subtract the 2, you'll get 70 neutrons. And that's C. Okay, now hopefully everyone was able to see that. I had it in the right spot. Anyway, so for number 5, we've got a solid labeled KCl, and it may be impure. All right, we don't know for sure. So what we're told is the student determined the percentage of chlorine in the sample to be 60% chlorine. The first thing you're going to do is find out what would be the percentage of chlorine in a pure sample of KCl. Chlorine is 35.5 grams. The total mass of a potassium and a chlorine would be 39 plus 35. That's 74. So you'd have 35 over 74. Now, 35 is exactly half of 70. So this is a little bit bigger than 70. So this is going to be a little bit less than half. So maybe around 48% chlorine by mass. So that would be if you had pure KCl. All right. Now, it says that the percentage of chlorine in this sample is 60% chlorine. So we have a bigger percentage of chlorine than we should. So it's definitely not pure KCl. It's going to have to be mixed with something that's going to have a higher percentage of chlorine than KCl would have, which means you're going to want the chlorine attached to something that has a very small mass, because that will give you a high percentage of chlorine. Between rubidium and lithium, lithium has the much smaller mass, which means this compound would have a much higher percentage of chlorine, and therefore it is a good idea as to what might be mixed with it. Number 6 is a really similar kind of animal. Acetone has a percent by mass of 62% carbon, so I'm giving that to you. Which of the following could be another ingredient in a nail polish remover if the percentage of carbon in the mixture is found to be 58%? So what we're saying is in the mixture there is a smaller percentage of carbon than there is in the original material. So the acetone has to be mixed with something that has a smaller than normal percentage of carbon. This doesn't look promising. This would be 36 over 44. That's like 75%, 30 over 40. So no way. That's a bigger percentage of carbon. C2H6O. So for this one, it would be 24 grams of carbon divided by 24 and 6 is 30, and this would be 46. So 24 is a little bit bigger than 50%. So this could be it. All right, that could be dragging that percentage down. Let's take a look at this one, C6H6O. 6 carbons would be 72 grams. And this would be 94 total, adding up all of these. Now that's much, much higher than 60%. So the only one that would drag the percentage down would have been C2H6O. Number 7, compared to iodine, tellurium will have. So always mark where they are on the chart. Iodine is to the right of tellurium. They're in the same period, so they will have equal shielding. So tellurium has one less proton, which means a weaker nuclear charge, which means a weaker Coulombic force, which is going to mean a smaller amount of energy would be needed to remove an electron, and the more they would be able to spread out, so a higher atomic radii. So I've done my analysis, so I'm looking for small ionization energy, big radii. That's big. A 5-gram sample of impure calcium carbonate, so I start by writing 5 grams calcium carbonate impure, but I do know that it contains 1 gram of calcium. What percentage of the sample must be calcium carbonate? Well, I'm going to use my 1 gram of calcium to figure out how much calcium carbonate has to be there. So I'm going to use my ratio, put it right underneath here. So the periodic table says I'm going to have 40 grams of calcium. I add all of these up, and that's 100. Folks, you guys, Veronica, Timmy, no talking. Okay, got it? So I'm going to put this and cross multiply. So 40x is equal to 100. I'm going to divide both sides by 40. So that goes in there 2 times to give you 80, and you'd have 20/40ths left over, which is 2.5 or 2.5 grams of calcium carbonate. So I've solved for x. 2.5 grams of calcium carbonate. Now I can find my percentage. Your percentage is the amount of calcium carbonate over the total mass of the sample, which is 5 grams. 2.5 over 5 is 50%. In the period 5 crew, it came out to 100%. mass spec. It's gone blurry all of a sudden. Alright, that's better. So what are we looking at here? We've got, looks like 5 different isotopes, but the average is going to be closer to here because this is the one that has the highest abundance. So if you look at the chart, the element that has a mass between 137 and 138 is barium. So that's letter B. This is a PES spectra. The highest binding energy is here. And this looks to be about twice as high of a peak than this one. So that's sulfur. The most common ion of sulfur, it's likely to gain 2 electrons to get an octet. So let's see. I went over this one in class, but you're comparing the 2s in carbon versus the 1s in lithium. The 1s is has much less shielding. In fact, it's right next to the nucleus. So this answer is going to have to do with the difference in shielding between these two. So the PES spectra of the 2s for carbon is a lower binding energy because it's got more shielding, less of a pull on it. So which one of these answers jives best? Two unpaired electrons. Silicon works. It finishes with 3p2. 2 unpaired. Oxygen also worked. It finishes with 2p4. And that would give you 2 unpaired here. Let's explain this data. Whoops, I'm not sure if I showed that. There you go. So 2 correct answers, A or D were correct. Which of the following best explains the data? So chloride is isoelectronic with argon. Fluoride is isoelectronic with neon. Neon has less shielding, which means stronger nuclear charge, equals stronger Coulombic force, which is going to result in higher ionization energy and a smaller radii. It's going to pull everything in tight, make it small. So that's why fluoride is smaller radii than chloride. So all I need to do is find an answer that jives. Chloride is more heavily shielded than fluoride, yep. Alright, down here, atoms of strontium combine with bromine in a 1 to 2. Of course they do. Strontium, if you look in the chart, will lose 2 to be 2 plus. Bromide will gain 1 to be Br minus. So what other element would also combine in a 1 to 2 ratio with strontium? Well, anybody who forms the same charge that bromine did, which would be anybody in the same column as bromide. And that's, of course, iodide, because they have the same number of valence electrons. What element can this be? These 2 electrons don't require much energy to remove, so they must be valence electrons. So element X will form an ion with a 2 plus charge. So if we combined it with chloride, we would need 2 chlorides to balance out the charge on X, so XCl2. Largest second ionization energy, talked about it in class. Now this is the second, so all of these would have already lost an electron. If sodium loses an electron, he's isoelectronic with neon. Chlorine loses an electron, he's isoelectronic with sulfur. Lithium plus loses an electron, isoelectronic with helium, and then oxygen. So if I want the highest ionization energy, I want the substance with the least amount of shielding and the highest nuclear charge for its row. The one with the least amount of shielding here is, of course, helium. So lithium plus would have the highest second ionization. Number 17. Why the electronegativity of phosphorus is 2.5 and sulfur is 2.6. I write how they are on the periodic table. Same shielding. Sulfur has an extra proton compared to phosphorus, so a higher nuclear charge, a stronger pull. Here, clearly 3 valence electrons, so this metal will form a 3 plus charge. The ratio with fluoride would be 1 to 3. For here, we're comparing phosphorus and nitrogen. Phosphorus is in the 3rd energy level, so 2 layers of shielding. Nitrogen is in the 2nd energy level, just 1 layer of shielding. So nitrogen has less shielding. So stronger pull on its electrons, which is going to make the radii smaller. Since there's a stronger pull on the electrons, it's going to take more energy to remove it. So it would have a higher ionization energy. C fits the bill. Most metallic. A metallic material is the thing that loses electrons easiest, which means lowest ionization energy, which means you're looking for someone with lots of shielding and very few protons for its row. The one that fits that bill, and you can check it out yourself, is germanium. Intensity refers to the number of electrons. So it would be less in oxygen because there are fewer 2p electrons in oxygen. The binding energy of peak C would also be less because even though they have the same amount of shielding, oxygen has fewer protons, so weaker binding energy. So if you're removing the 1s electrons, you would be removing them from peak A. Just to show you where the points were earned here on that. show you where the points are. 1, 2, 3. This is going for this calculation. Converting this into kilojoules per mole. First to kilojoules. Since kilojoules are bigger, there's always going to be 1,000 less of them than there are joules. So I'm going to divide this by 1,000, which is the same as making it 3 powers of 10 smaller. Now, this is for an individual electron. If I want it for a mole of those, there are 6 times 10 to the 23rd electrons in a mole. Okay? So this will give me my energy in kilojoules per mole. And 1 point for getting it in kilojoules, the other point for getting it in kilojoules per mole. Percent by mass of carbon and morphine, you would simply add up the mass of 17 carbons divided by the mass of everything, and then multiply by 100, and you would have the correct answer. The hydrogen to oxygen mass ratio, you'd find the mass of hydrogen, which is 19 grams, divided by the mass of oxygen, which would be 3 times 16, which is 48 grams of oxygen, and that would give you a ratio. How many grams of morphine could be produced from 1.6 grams of oxygen? Set up a ratio. X grams of morphine. So here you put grams of oxygen, here you put your grams of morphine, and we know there'd be 48 grams of oxygen for whatever the total mass of morphine is. That's the mass that you would have added up here. Do your cross multiplication, and you'll have your grams of morphine. How many grams of carbon would be needed to react with 1.6 grams of oxygen? So I have 1.6 grams of oxygen. I want to know how much carbon I would need. Well, I know in morphine there's 48 grams of oxygen for every, whatever 17 times 12 is, for your grams of carbon. So that would be the mass of carbon in morphine. You cross multiply, and you'll have your grams of carbon. Easy. Lastly, for our heroin, it is an artificially modified, more addictive version of morphine. They're all very addictive. Stay away. A student examined a potential impure mixture of morphine to see if there was heroin present and listed their data. So what's the percentage of the sample? So you do 3.05 grams. A lot of you lost points because you didn't label anything. Divided by 122.4 grams of the mixture. And you would get, times by 100. And you get your percentage of nitrogen in our mystery sample. What percentage of morphine is nitrogen? So for this, you just scooch over to this side. We've got 1 nitrogen in morphine. So nitrogen has a mass of 14 over the total mass of morphine, again, which came from the other side, times 100. All right. Now, I remember this, is that this number, whoops, that's what you do. This number right here was smaller than this number. So could this sample be contaminated with heroin? To know that, I would need to have seen that you had done the legwork to determine what would be the percentage of nitrogen in heroin. Now, just looking at the formula of heroin compared to that of morphine, the formula for heroin is a lot bigger, which means you've got the same amount of nitrogen, but you've got a much bigger mass here, which is going to mean a smaller percentage of nitrogen. And that's all you need to really say. Could have calculated it, but since the percentage of nitrogen is less in heroin than morphine, you can certainly view heroin as a potential candidate for contamination because the percentage of nitrogen in the sample was less than that of morphine. Since heroin has a smaller percentage of nitrogen than morphine, it is an excellent candidate to have been the contaminant in our mixture. And a lot of you explained that really well. This last one we're going to go over at some point, maybe this week in class. I'm not sure, but that'll be something that I'll save for class. All right, so there's the exam. Check it out and make sure that you can do everything on it.